Okay, let's talk about 7.2 number 11. Where am I? 7.2 number 11. Okay. Yeah, this is an interesting one for sure. So, um, yeah, the only thing I could think to do would be to integrate by parts. I can't even think of a u substitution that would be helpful here. So, um, yeah, so let's do it. So let's integrate by parts. I kind of like just going straight to the tabular method. If you like doing it differently, that's fine. But I like going straight to the tabular method because if I need to do this multiple times, then I can just do it all at once. But that said, on this particular problem, I think it is helpful to kind of like redo it. I'll show you what I mean. So now if we're trying to choose what to differentiate and what to integrate, in this case, it's like there's only one function. One thing that did occur to me is that we could try to write this as ln of x times ln of x and then differentiate one and integrate the other. The only problem is we don't know off the top of our heads what the integral of ln of x is, so that's not really going to work out. Which means we've kind of just have to differentiate the whole thing. So I'm going to put the whole thing over here, ln x squared, and then this is just going to be dx. So if I differentiate this, I'm going to have to use chain rule, so I'm going to get 2 ln x to the first power times 1 over x. So maybe I'll write it this way. For the purposes of differentiating again, it would be helpful to write this as maybe 2x to the negative 1 ln x, right? So this would be 2 ln x times 1 over x, okay? And then for the integral, I'll call this thing x, okay? So now, if you think about what you're going to end up with, if you stop there, you're going to end up with x times ln of x squared, and then you're going to have to integrate 2x to the negative 1 ln x times x. Well, that's kind of nice because this x and this x to the negative 1 will cancel. So all you have to integrate is 2 times ln of x, which isn't bad at all. We can do that if you don't have it memorized. I don't have it memorized personally because I always know that I can just integrate it by parts. But I think we did that example together. I think, maybe not. But we can integrate that by parts again. The trouble is if I try to just keep going with what I have here, so if I try to take this a step further, I think we start to get into the weeds pretty quick, right? So let's see, if I differentiate again, I'm going to treat this as my first function f, and this is my second function g. So I'm going to do derivative of the first, which would be negative 2x to the negative 2 times the second, plus the first. The first would be 2x to the negative 1 times the derivative of the second would be 1 over x, or x to the negative 1. So I'm just going to call that 2x to the negative 2. All right? So there's my derivative again. And if I integrate again, I get x squared over 2. And that's actually not bad because, again, if I think about multiplying these together to see what I have to integrate, the x squared here is going to cancel the x to the negative 2's there. And so all I'll have to integrate, oh, and this 2 will cancel that 2 and that 2. So the only thing I'll have to integrate would be negative ln of x here, and then just a 1 there. So that wouldn't be too difficult to integrate. But what I want to point out is that it's not any easier to integrate than if we had stopped at the previous step, right? If we had stopped at the previous step, what we would have to integrate was 2 ln x, right? Here we have to integrate negative ln x plus 1. So it didn't make things any easier. Now maybe if you continue on in this path, you might end up at a place where it gets easier at some point, but I kind of doubt it because I don't think you're ever going to lose this ln of x term. Because from now on, every time you integrate, you're going to have to use the product rule. And so ln of x is always going to be there, right? It's never going to disappear when you differentiate. Which means that inevitably, you're going to have to integrate the natural log of x, right? You're going to have to do that at some point. So rather than kind of continuing on here, because I don't think it's going to lead anywhere useful, I'm just going to stop at this previous step. So to answer Jordan's question, because Jordan asked, like, is there a rule of thumb? Like, how do I know where to stop? I mean, experience, I guess, is the answer, right? You just have to practice and kind of figure out when a good place to stop is. And in this case, in the lecture, I kind of gave some guidelines. I mean, like, if you notice a repeat where the thing that you end up having to integrate is more or less the same as what you started with, well, then you can kind of like algebraically solve for the integral. Or if your derivative is going to go down to nothing, then you can just keep going out that way. But otherwise, it's just like you do this until it becomes not useful anymore, right? So like doing the first step was useful for us. It made the integral easier. If we continue going, it's not going to get any better, and so it's not really wise to continue. So anyway, so if we piece this together now, this is going to be x times ln of x squared, and then minus this x cancels that x to the negative 1, so integral of 2 ln x. I'm going to go ahead and pull out the 2 now. So minus 2 times the integral of ln of x dx. Now, as I said, if we continue going this way, it's not going to get any easier. On the other hand, you know, we still haven't finished the problem, and we don't know how to integrate ln of x without using differentiation by parts. But what I'm going to do is I'm going to start with a fresh slate. I'm going to do this again with just ln of x over here, and then dx on the other side. See, the problem is that because I had ln of x times 2x to the negative 1, I was going to have to use product rule, which means the ln of x was never going to go away. But if I can start over with a fresh slate here, derivative of ln of x is just 1 over x, integral of dx is just x, and notice when I multiply these together, well, I just get 1, right? And so that's really nice. So, okay, so I've got x ln of x squared minus 2 times x ln of x minus the integral of just 1 dx, right? And that integral is easy. So then we can say it's x ln of x squared minus 2x ln x plus 2x plus c. And that's that. This one is a fun one to differentiate. Like, so you can differentiate this and see that you end up back here at ln of x squared. But it does work. You get a lot of cancellations, obviously, so it's kind of nice. But that's that one. And again, it's like guidelines for when to stop with tabular method are, first of all, if you know that your derivative is going to go down to 0, then just keep going, right? Just keep going until the derivative goes to 0, right? That's by far the easiest thing to do. If the derivative is not going to go down to 0, but you notice that like the thing you're integrating is a repeat of what you started with, or a repeat of something earlier on in the process, then you can probably stop and solve for the integral algebraically. We did an example like this in the lecture. Or if neither of those things are going to happen, then you just stop whenever it becomes like not useful to continue. And in this case, that happened kind of after the very first step. We ended up having to do it again, but we were able to hone in on just ln of x, and so that made it easier. So anyway, I hope that helps, you know, give you some guidance there. But overall, like really the true answer to like how do I know when to stop is, well, you practice, right? You practice, and then you kind of figure out when to stop on problems like this. That's that.